All right, last time we started taking a look at systems of equations in two variables. In particular, we talked about the fact that there are three different options for how two lines can sort of interact in a plane. They could intersect, they could be parallel, or they could be actually just the same line themselves. And we looked at finding whether or not a particular proposed solution actually works. We talked about the fact that it has to work in both equations. If it only works in one, that's not good enough. And so we kind of left off last time with me making the comment of, great if somebody just proposes a solution to you, yay, but what if you were trying to figure out what it is and you don't want to guess infinitely many possibilities to test everything, right? So how do we find it directly? So there are three ways to find solutions to these. Three that we're going to talk about. There are other ways too, but there are three we're going to talk about. The first one is graphing. So for those of you who are super visual people, graphing can be useful. If you've already been given a graph to start with, it's super nice, right? Because you can identify from the graph. But sometimes it's harder from a graph too, because it may not cross at whole number values. You know, it's hard to decide, is it crossing at 1/2 or 1/3, that kind of stuff. So graphing can be a little bit tricky. Substitution is the idea of taking one equation and solving it for a variable and then plugging it into the other one. And we'll do an example for that one. And elimination is the process of adding two equations together so that one of the variables just gets eliminated. And we're going to see how we can make that happen. Most of your problems in your homework, if I'm remembering right, don't tell you how you have to solve them. So if you're not told how you have to solve them, you have a choice and you can choose whatever way you'd like. You do have to show work for it. So if you're going to do it by graphing, you do have to draw the graphs and show where they're crossing. If you're going to do substitution, you got to do actually the process that I'm going to show you for substitution or the process for elimination. So you still have to show your work. You can't just plug things into a calculator or something like that. That's not what I'm talking about. But for the most part, you have quite a bit of flexibility in how you choose to solve the problems. That said, sometimes problems are really nice to solve one way and really horrible to solve a different way. So if you absolutely love substitution, there may be a time where you're like, there's a lot of fractions going on here or ugliness that just substitution is not my thing right now. So some problems lend themselves really well to one or the other, and some are just, about even either way. So we're going to start first with graphing. The one that I have chosen is kind of not so friendly, so I kind of wanted to give you an example of one that's not so friendly because you saw one that was friendly. It was our very first slide. The only reason this one's not so friendly is because it's equal to -22, which is kind of a big number. So my graph has to be fairly large. That's the only reason this is not so friendly, is the largeness of it. Now, the other thing that's maybe not quite so nice, at least how this problem starts out, is that both of the equations are written in what's called standard form. Now, we didn't talk a lot about standard form because the reality is it's not very useful. I mean, it has its place in the sense that it looks nice, I suppose, when you're looking at it. You've got whole number values, you have a positive, usually it starts out with a positive x value and then maybe the positive or negative on the y value. It lines things up, x's and then y's and then constants, all that looks, but it's not very useful. And so when we're working on graphing, the first thing that we would need to do to find it to be useful, at least usually, would be to solve it for y. And in both of these cases, these do solve pretty nicely for y. So on the first one, if I have 2x plus y equals 10, and I want to solve it for y, I'm just going to subtract the 2x over to the right-hand side. That's not too bad. On the second one, I have -5x minus y equals -22. So I can add the 5x to the other side. But then I need to divide or multiply by -1 to remove the negative from in front of the y. So I need to change all my signs. So this is y equals -5x plus 22. Now, this isn't the only way to graph lines, obviously. You could pick two random points and connect them, and that'd be okay. But probably for most of us, this is what we think of when we think of graph a line. Get it into y equals, and then use slope and y-intercept. All right, so we're going to take each of these equations and we're going to graph them. Now, I have the advantage of having a grid. You guys don't. So as we're graphing these, it'll be easier to see where mine cross probably than yours will, in terms of, you know, if it crosses at a whole number value. So first things first, I can't draw straight lines. Well, I can draw them straight. I just can't draw them on the grids, so I'll move them. So here's my graph. And my first equation is y equals negative 2x plus 10. So what's my y-intercept? Yeah, 10. Sorry, I'm going to need to make this really tall in a minute here. It's got to go all the way up to 22. So I'm not even sure I'm tall enough as it is. All right, 10. Two, 4, 6, 8, 10. All right, and what was my slope? Negative 2x. Okay, so what is negative 2x telling me? Or what does the negative 2 tell me on the slope? It would be rise if it were positive, but it's negative, so we're going to fall 2. So we're going to drop 2 and over 1, right? So because eventually we're going to look where things are going to cross, it wouldn't necessarily be a bad idea to plot several points before we connect them, just because it might make it easier to see in terms of your graph when we get there. So we have several maybe plotted, just going down the line. So this is one of my graphs. I didn't mean for that to be dotted. Let's change that. Okay, so there's one of my lines. My other graph, unfortunately, is the one I was referencing, is how it starts at 22. It's not especially friendly, but that's why we made the graph as tall as we did, so I'm hoping it will catch it. If not, we'll have to move my graph down. So let me see here. Nope, it's not tall enough. All right, so I'm at 18. Nice. Now I'm off my screen. All right, there's my other one. 22, and what was its slope? It's negative 5. So I'm going to go down 5 and right 1. So that would be here. Down 5 more and right 1. And eventually I'm going to catch up because, right, I'm doing this faster. And then on my red graph. And here it is. So my graph looks something like that, crossing there. And again, with a grid, it's easier to identify where that's happening. Can you tell from my graph where I'm at? What's it look like? Nobody knows. Count for me. What is it? 4.2 is right. Yep. It's at 4.2. Okay. The ones where I think there may be one or two where they give you an option of graphing and they tell you to use a graph or something like that. They'll put a grid on there for you. That's nice. If for some reason you don't want or you want to do more of them in graphing mode because you have a choice, you can print out grid paper from online, or you can purchase grid paper at a store, of course, too. So if you don't like drawing it freehand on notebook paper, that's another option. Okay, so that's one way to do it, is with graphs. Sound good? Okay. Like I said, one of the serious limitations, though, is aside from this one being ugly because I had a big value of 22, it was still very friendly because it crossed at one of the grid markings, right? But not all answers do. Sometimes answers actually give you values that are fractional or decimal, and it doesn't show up very clean on a graph, and so there is a limitation there. All right, this is our second method. Our second and our third method both require a little bit of, they don't require it, but I choose to present them as though they're sort of step-by-step operations. So method number 2 is substitution. With substitution, what you do is you take one of the equations, your choice, and solve it for one variable, again, your choice. You substitute the expression into the second equation, and then you solve it for step 3. Step 4 is to back substitute to find the other variable. And step 5 then is to write the solution as an ordered pair or with context or units. So in this section we're looking at ordered pairs, but in the next section we're looking at context or units. You have to answer the question as it was presented. Okay, can I switch screens? Okay, so substitution is more rigid, but there is flexibility that still allows you to make some choices as you're considering your equations. The first place of flexibility is the very beginning. You get to pick the equation and you get to pick the variable you solve for. There are choices usually that are nice and choices that are usually not nice. For example, if I solved the second equation for x, that would not be very nice. Why? Because there's a 5 in front of it, a 22 at the end. I'm going to end up with either decimals or fractions. That's not especially friendly. So usually when we're choosing which equation to solve for which variable, we'd like to choose an equation that has a coefficient of 1 on one of the variables and choose that variable. So for instance, choosing y in either equation is not too bad. Okay? The first equation might be a little bit more friendly because the y is also positive. So that's where I would probably say let's begin. Sound good? Okay. So you don't necessarily have to label this as step 1, this is step 2, this is step 3, but if it helps you to organize your thinking, then by all means do so. I will, just so that we make sure that we're all on the same page. So the first step is to take an equation. I'm going to take the first equation and to solve it for one of the variables. So if I solve the first equation for y, this is y is equal to negative 2x plus 10. You guys recognize this is the same equations that we just did, right? So our expectation is we'll get the same answer. So that's step 1. Solve one equation for one variable. Step 2 is to take the second equation, whichever one you haven't manipulated at this point, and it's to substitute. So what does that mean? Well, it means that everything that y is now going to replace y. So previously I had negative 5x minus y. Now I will have negative 5x minus the thing that y equals, the expression, which is negative 2x plus 10. So it looks like that. And the cool thing is at this point with substitution is that that becomes an equation that has one variable. And you should be able to solve it with the techniques that we've been using all semester. Okay? So we distribute if we need to, we clean things up, we combine like terms. Eventually at the very end it's going to say x equals a number. So if I do that, I would have negative 5x. I'll distribute the negative. So this is plus 2x minus 10 equals negative 22. What can I combine? Yeah, the x's. So negative 5x and positive 2x would be negative 3x minus 10 equals negative 22. And then what? Add a 10. You bet. So negative 3x equals should be negative 12. Negative 22, positive 10. And then if I divide by negative 3, what's negative 12 divided by negative 3? Yeah, x equals 4. So this is steps 2 and 3 because once I started solving, that was step 3. Step 2 is the substitution. Right here is where step 3 would have been. Step 4 says something like back substitute. Back substitute means to take any equation, but again, some choices are nicer than others, and figure out what the other variable is. So in particular, it's really nice to take this equation to do that. Why? It's already solved for y. Okay, any of the other equations will work, but this one's kind of nice because it's already solved for y. So step 4, I'm going to take that equation that's already solved for y, and I'm going to plug in the value that I just got for x. And again, I'm down to one variable. No matter which equation I picked, I would be down at this point to one variable. I have y equals negative 8 plus 10, or y is 2. The last thing to do is to write the answer in an appropriate way, depending on the problem. So in this problem, these are just two equations. I don't have any context or anything to go with, so the appropriate kind of representation for the answer would be as an ordered pair. So it's the ordered pair 4, 2. When we get into the next section, we're doing application problems, and there will be context. You know, it'll be $2 and 4 hot dogs, or I don't know, something like that. Whatever it is, we're going to have different context to our problems. Right here. Yeah. And then my x was down here. Okay. Any questions before I show you the last method? Okay. Our last method is called elimination. And elimination eliminates a variable. And it does it, sometimes this is actually called the addition method as well. Our college algebra textbook that just a straight college algebra class would use calls this the addition method. Most books call it elimination. So what you do is you line up the variables, right? So it goes x's, y's, constants, standard form. You multiply one or both equations to get the same number and opposite signs on one variable. So like you want one of them to say 5 and the other one to say negative 5. You want one of them to say 8 and the other one to say negative 8. One of them to say 1, the other one to say negative 1. Same number, opposite signs. Because the cool thing is when you add 5 and negative 5, or 2 and negative 2, or 1 and negative 1, you get 0. And when you do that, it eliminates that variable. So 2x and negative 2x is 0x, or just 0. After you have eliminated a variable, you will have one variable left, and you can solve. And then you back substitute it into an original equation, just like our other method. And then the solution with ordered pair, notation, or units. Okay, can I move to an example? Almost. Good? All right. Let me just make a comment. We could use the same example again. The reason I didn't want to is because it's actually really like super friendly because these already have the same sign or the same number and opposite signs. So if I were to do this problem, I wouldn't have to multiply anything. These are already lined up, x's, y's, constants. If I add them together, this would give me negative 3x. These would add to 0, and I'd get negative 12. You see how friendly this one actually is with elimination? Like super friendly, okay? However, it's also not too bad with substitution. This problem, however, is not friendly. It's terrible for substitution. I don't want to solve either of those equations for any variable. Do you? They look awful. There's a coefficient that's not 1 in front of every term. And no matter what I divide by, 7, 9, 2, or 3, I'm going to end up with fractions or decimals when I do so. And that's even worse. Right? It's just going to be so messy. So this is a really good example of one where elimination's really just your best bet. It's going to be the cleanest way to do it. Now, what we'd like to do is we'd like to compare, and you have a choice. You can compare the 7 and the 2 and recognize that one option is I could multiply here 2 and here 7 and multiply 1 by a negative, and they'd both be 14s, right? That's a possibility. The other possibility is to consider the negative, or the 9 and the negative 3. Now, the 9 and negative 3 actually have a multiple sooner than multiplying them by each other. What could I multiply by which equation to get these to match? Yeah, if I multiply the bottom equation by 3, I'll get a negative 9y compared to my positive 9y on top, which is exactly what I want. So that's probably your best, or maybe not best, but your quickest option for elimination on this one is to multiply the second equation by 3. Okay, so number 1 was to line things up. That's already done. Trey?
So are we multiplying the whole equation by 3?
We are. Yeah, anything you multiply in an equation has to be the entire equation. So these are already lined up, x's, y's, constants. That's already done. Second thing is to multiply. So we're actually on to step 2. Step 1's already done for us. Step 2, and it often is. It's not often that we have to deal with it, but sometimes. So we're going to multiply, like Trey asked, the second equation by 3. So 2 times 3 would be 6x. Negative 3 times 3 would be negative 3. I'm sorry, that's what's wrong. Here we go. Negative 3 times 3 would be negative 9. And then this one's kind of big, but 22 times 3 would be what? Yeah, 66. That's step 2. Step 3 is to simply add them up column-wise, right? Just like old school addition. Think first, second grade here, right? So 6x and 7x add up to 13x. The 9y and the negative 9y, the whole point is they add to 0, right? So they're gone, they're eliminated. And then negative 1 and 6 would be 65. So this is step 3, is to add them together. I think it was step 4. Yep, step 4 is to solve that equation. So 13x equals 65. What would I do? Yeah, I divide by 13. What is 65 divided by 13? Feel free to grab a calculator if you're not quite sure. 5 is right. Good. So this is step 4 that we're working on right here. We've solved the equation. But I only know x. And I need to also know y. So step 5 is finding that y. Now, unfortunately, when we did this problem over here, there was an equation that was really nice, like y equals, and we could use that. That doesn't happen when we do elimination. You just have to pick one of the equations and plug it in. So, do you have a favorite equation you'd like to use, number 1 or number 2? 2's got a little bit smaller digits, so I would probably go with 2 as well. So, we have 2x minus 3y equals positive 22. And I know that my x is 5. So this is 2 times 5 minus 3y equals 22. 2 times 5 is 10. We'll subtract a 10. And divide by -3. That's step 5. What is step 6? Yeah, it's the ordered pair. It's the x coordinate and then the y coordinate. So x is 5, y is -4. And we're done. How can I make sure that that's really the right answer? Plug it back in to both equations, right? Yeah, just like we did last class period, right? When we were checking to see if something worked. So literally you could check all your homework problems, and you could check them pretty quickly if you just grabbed a calculator to check them, plug them in real quick, and make sure that you have the right solutions. So it's a nice feature.